All right, homework number one, problem number two is asking us to prove this statement in two different ways. This is P implies Q is equivalent to not Q implies not P. And again, P implies Q is basically saying if P is true, Q must be true. So that's what this statement, this implication means. So for a more concrete example, if it is raining, this would be our P, right? Our P, if it's raining, then the ground is wet. And this would be our Q. The ground is wet would be our Q. So if this thing is true, then this thing has to be true. That is what the implication means. So all I've done is draw out a truth table, and we want to make sure that we have every possibility here. So we can write true or false. I usually do zeros and ones because it's easier to remember. It's really just writing in binary. 0, 0, 0, 1, 1, 0, 1, 1. But you can also do false, false. And it doesn't matter which one you do. They mean the same thing. But basically, this is every possible combination of P and Q. So in this example where we say if it's raining, the ground is wet, false, false means that it is not raining and the ground is not wet. False, true means it is not raining, but the ground is wet. So think about this logically, right? If you go outside and you see that the ground is wet, but it's not raining, does that mean that the next time it rains, the ground won't be wet? You can't overturn this entire statement basically saying that when this happens, that this happens based off of one observation where the premise of it isn't even true. There could be many reasons why the ground is wet. Maybe somebody had their sprinklers on, but the next time it starts raining, that doesn't mean that the ground is suddenly going to be dry. So in order for this entire statement, this entire concept to be false, we need this premise here to be true. So what we say is that this is going to be vacuously true because we can't prove that it's false. And the same thing here. If this is going to be false, then we know that this is going to be true. Now, in this particular scenario, we say that it's true that it's raining, but the ground is not wet. And if that is the case, then that does overturn the implication. Because if you're claiming that this is always true, and this particular scenario is an example where that is not true, then clearly this statement is wrong. So we're going to write false. And then the only other observation is that it is raining and the ground is wet, and that only confirms what we have here. So we're going to write that true. So here you can see our Q is false. All we're going to do is convert that into the opposite. We're going to make it true. This is true. We're going to make it false. And then we're going to do the exact same thing with P. We're going to take false and convert it to true, false, convert it to true. And then finally, we can look at the implication here. This is a different implication. Not Q implies not P. And we're only looking at not Q and not P. And if both of these are true, then we can say that this is true. This is going to be true. Now here, again, we have this condition where the general premise of the implication is false. So therefore, we have to say that it's vacuously true. Because if not Q is false, then it doesn't really matter what not P is. And now in this case, we have that Q is true, not Q is true, and not P is false. At that point, this is false. And then finally, we have false and false. And again, if not Q is false, then we have to assume that it's vacuously true. And you can see here that we have the exact same truth table for P implies Q as we do for not Q implies not P. Therefore, they are logically equivalent. So that is one proof, one way to prove it. The other way to prove this requires knowing in advance that P implies Q is logically equivalent to not P or Q. This is the or symbol. And we can use truth tables to prove this statement the same way that we just proved that P implies Q is equivalent to not Q implies not P. But we're going to assume that we, memorized it. But what we can do is essentially copy this not Q implies not P here. And you can see I've got a Q here. All I'm doing is essentially plugging that in to be my value of P. Rather than P, this is going to be a not Q. And then here, instead of this Q right here, I'm going to use not P. But if we look at what's going on here, we have this equivalency and we have a not sign, so we're going to just copy that over. And then whatever this first term is, this P here, we're just going to copy that. That here is not Q, so we're just going to copy that over. Then we have an or symbol, so we're going to copy the or symbol. And then finally, we have a Q. So we're not adding a not or anything. We're just going to copy whatever's right here, not P. And now you can see that we have not Q, which is the same thing as Q. And then you have the or symbol, and then not P. And what you can see is we have the exact same thing here and here. The order doesn't matter. Q or not P is the same thing as not P or Q. So therefore, we can prove that that is equivalent.